So in the last few lectures, we have talked about linear programming, right? We talked about the simplex algorithm to solve linear program, some geometric properties like what is an extreme array, what is an extreme point for a polyhedral set. Then we talk about linear programming duality, right? So as you can imagine, linear programs is probably the simplest convex constraint optimization problem, since the objective is linear, the constraints are linear. And then before we talk about general convex nonlinear program, we will spend one lecture on what is called conic program. So why do we care about conic programs? So conic programs involve problem where the problem is described by something called a convex cone. We will show you that in the next slide. And the most commonly used conic programs include linear program itself is a very special case of conic program, and conic quadratic program, and then what is called semi-definite programs. So why they are different from general nonlinear problem is that these conic programs are very well structured. They have special geometric properties, just like linear program, polyhedral set have special geometric properties. Conic set also have very interesting properties, right? And in the, I would say, past 2 decades or so, conic program has been a very hot research area in optimization. So since linear program has relatively been well studied, and general convex nonlinear program has been well studied. But a lot of research has been focused on this special class of problem. Of course, if you read the recent research papers, there are many papers. If you go to, especially if you go to an optimization conference, there will be sessions dedicated to conic programs. We will only spend one lecture. If you are curious about that, or if your research is related to conic program, you can read some of the reference listed at the end of this class. Okay, and it has very wide applications, like in control theory, finance, signal processing, and then even in some of the machine learning algorithm, conic program like semi-definite programming is used. Okay, so before we introduce the formulation for a general conic program, let's review some concept we have discussed before. Right? So what is a cone? A cone is a set such that for any x in this set C, t times x for all t greater than or equal to 0 is also in the set C. Right? That is definition of a cone. And the convex cone denotes a set that is a cone. It is also convex, right? So here, if you consider this particular set, right? Let's say this is a x-axis, this is a y-axis, and then the feasible region are these two rays here, right? So if you consider these two rays denoted in red, this set is a cone, right? Because you pick any point, t times that point, t greater than or equal to 0, is also in that set, right? But this set is not convex. So a convex cone means if you take any 2 points in the set, then t1 times x1, t2 times x2, where t1, t2 greater than or equal to 0 is also in the set, right? And clearly, by definition, this set is also convex. Why is that? Here, right? The idea is you pick any arbitrary x1, x2 in the set, pick any arbitrary t1 and t2 greater than or equal to 0, it is in the set, right? Why this set is also convex? Yes?
If you make t1 and t2 instead of lambda and 1 minus lambda, then you're...
Yeah, exactly, right? Because, convex is a more restrictive definition, right? When you have t1 and t2 greater than or equal to 0, and the summation of t1 and t2 equals to 1, right? But here we don't have the summation equals to 1, so therefore you can choose any convex combinations you wish for using this definition. Okay. And remember, we also talk about Conic combination. If you pick k points or k vectors in Rn, the Conic combination means you can take lambda times x1 plus lambda all the way lambda k times xk, where lambda i's are greater than or equal to 0. Right? This is called the Conic combination of k points. Right? So the Conic Hall collects all the Conic combinations. Right? Remember, we had a slide where we show what is a Conic Hall, what is the convex Hall, what is a linear Hall of two vectors. Right? So the Conic Hall of these two vectors is essentially this green region in between. Right? That's a Conic Hall of this set. Okay, so here's the definitions to keep in mind. Right. So now let's define another concept called proper convex cones. So a proper convex cone is a cone, of course, right? And then it has the three properties as well. First, it is a closed set, right? Everyone knows what a closed set is. Anyone knows what an open set is? What is an open set? An open set is you take any point in the set, you can draw a ball that is small enough, like epsilon with epsilon radius, and then that point, that small ball is still in the set. Right? That is an open set. And the closed set is if you take the complement of open set, that is a closed set. Okay. Yeah, and this set is also pointed, means if you take k intersected with minus k, it is only intersected at 0. Okay, so think about a cone that is not pointed. Right, so if you consider, for example, a cone like a hyperplane that passed the origin, right? So let's think about this set of the hyperplane, right? Take minus k, right? And then minus and k will intersect by a line, not just 0, right? So this cone is not pointed, and it has non-empty interior. Right? That's a trivial summary. You don't want a cone with non-empty interior. Okay, so you can just take it as granted. The cones I will show you today are all proper convex cones. Yeah, so I will show you a few examples of proper convex cones and then how they are related to optimization problems. Now, here's another concept called the dual cone. Right? This may sound abstract when I first introduce that. Then I will derive this dual cone using Lagrangian dual later on. Okay. So a dual cone is a set of vectors V in Rn, such that for all the elements in the original cone K, the vector V has a non-negative inner product, with all the elements in the original cone K. Okay, so that's a definition of the dual cone. You may find it a little bit counterintuitive, but then I will derive the dual of a conic program later on and show you why we need this concept later. Okay. Yeah. So there is a theorem saying if K is a proper cone, then the dual cone is also proper. Right? We won't show the proof of those theorems. We will show you a couple of proofs, but not all the proofs in this lecture. Okay. So here's some other notations. So if we see vector x, this notation is like greater than or equal to y by cone K. Right? What does this notation mean? That means if you take x minus y, then this vector is in cone K. Right? So if you consider a very special case of cone, which is let's consider a cone being x greater than or equal to 0. This is just the most naive cone you can think about, right? And then if you consider, let's denote this in green color, right? So if I say x greater than or equal to y by this cone k I just defined, that means essential x minus y is in cone k, where k is saying x minus y is greater than or equal to 0. Right? So this is essentially saying x minus y greater than or equal to 0. Right? So this is nothing but saying x greater than or equal to y, right? As you can see here. Right? This is if the cone is defined as this particular cone. So as you can see, this notation is sort of a generalization of inequality, the inequality we are familiar with. Right? It generalizes the greater than or equal to cone into any arbitrary convex cone. Right? Okay, and then if you see something like x strictly greater than y subscript cone k, that means x minus y is in the interior of cone k. Right? So you can also go back to this particular constraint and think about what is the interior of this cone. It is nothing but x strictly greater than 0, right, for this particular cone. Right? So as you can see, it is also a generalization of strictly greater than 0 constraint. Okay, so if you, once you find it non-intuitive, you can come back to this very simple example and try to understand what it means. Now, what is conic programming? So let's consider K be a proper convex cone in Rm, pointed closed with a non-empty interior, and then give an objective C. Right? C is in Rn, and the m times n constraint matrix A and the right-hand side vector B. Consider the following optimization problem. C transpose X subject to AX greater than or equal to B. Right? So remember, what does AX greater than or equal to B means here is AX minus B is in this convex cone K. Right? One obvious observation is linear program is a special case of conic program. Right? So why that is the case? So linear program can be considered as a cone which is y greater than or equal to 0. Right? So if you consider the linear programming cone, the constraint reduces to AX greater than or equal to B. Right? So that's what linear program is. But now we are talking about any general convex cone K. Okay? Any questions here? Yeah.
So we have to have a linear objective function.
Yeah, we have to have a linear objective function. Yeah. Subject to a constraint, it is a linear transformation of X, but then the inequality are defined based on a cone instead of based on greater than or equal to 0. Right? As long as K is a convex cone, it works. Yeah.
What is the meaning of pointed?
The meaning of what?
Proper convex cone which is pointed.
Oh yeah, pointed means this definition, right? If you take K and minus K and they intersect, they only intersect at 0, the origin, right? Like this example I gave, if you take the minus of this half space here, it is not, the intersection is not pointed because they intersect by a line, not a single point there, right?
X greater than 0 is pointed cone.
Yeah, so X greater than or equal to 0 is a pointing cone. If you take the minus of that cone, it's the other origin they intersect by. Yeah. Okay. Yeah. Now, So now let's use the concept we learned from last lecture to derive the dual of this conic program. Let's think about this step by step. Right? Let's try to recall how we derive the dual of a linear program. Right? remember we use a Lagrangian multiplier, right? To multiply the linear inequalities, or sometimes you have linear equalities, right? So what is the sign of this? Recall last lecture, right? So if you have minimize C transpose X subject to AX greater than or equal to B, right? This is a linear program. Let's recall what we did in the previous lecture to derive the dual, right? So first, you multiply this inequality constraint by lambda, right? And then the signs of the lambda is consistent with the signs of this inequality constraint, right? So that's what we did from the previous lecture. Then you got this Lagrangian function d lambda, which is minimizing x, C transpose X plus lambda times B minus AX. Okay. So recall, why do we need lambda to be greater than or equal to 0? Right? So the reason we want lambda to be greater than or equal to 0 is because for any feasible solution to the original problem, right? So for any feasible solution to the original problem, this term is less than or equal to 0, right? And we want the dual to provide a lower bound of the original problem, right? Since for any feasible solution, this is less than or equal to 0, that's why we set lambda to be greater than or equal to 0, right? That's sort of the rationale deriving the Lagrangian dual in LP. Then we were saying it is already a lower bound, right? But then now you are minimizing over x, right? So let's gather the linear terms here, which is C transpose. Oh yeah, this should be a lambda transpose minus lambda transpose A times x plus lambda transpose B, right? And then since x is unconstrained, right? After you dualize the inequality constraint, x is unconstrained. So then this term must be 0, right? Otherwise, it will go to infinity. We are not interested in a trivial lower bound, right? Minus infinity. So that's why in the dual, what we have is minimize. Actually, you want to find the lambda that give you the tightest lower bound. That's why you are maximizing over lambda transpose B, and lambda is greater than or equal to 0. C transpose minus lambda transpose A equals to 0 transpose. Right? So that's a dual we derived in the previous lecture. Okay. So now let's think about how do we generalize this Lagrangian dual to a conic program. Okay. Again, so let's think about how to define the d lambda function, right? So if you are minimizing over x, C transpose X plus lambda times B minus AX, right? So now what I know is this particular term is in minus k, right? Because by definition, AX minus B is in con k, right? That's why B minus AX is in minus k, right? Okay. Now, I want to pick some lambda such that for any feasible solutions, a feasible solution meaning B minus AX is in con k, or AX minus B is, B minus AX is in minus k, and AX minus B is in k, right? For any feasible solution, these terms gives you a lower bound, right? So how can you choose such a lambda? Right? So the way you can choose the lambda, I would argue, is the following. You should choose lambda in a set such that V transpose U is greater than or equal to 0 for all U in K. Why is that? Because you want this term to be negative for all the AX minus B in K, right? Now, in order for that to hold, that is essentially this condition. For any vector U in K, so this U thing here is your AX minus B, right? So for any of the vectors in K, V has to be greater than or equal to 0 in order for this term to be a lower bound, right? So this is equivalent to saying lambda times B minus AX is less than or equal to 0, right? For any feasible solution you pick. That's sort of the rationale of the dual cone. Okay, so recall that how did we define the dual cone? It is for all the U in the original cone K, U transpose V must be greater than or equal to 0. Okay, so therefore, we need to pick lambda in the dual cone for d lambda to be a lower bound. Right? So the dual cone is essentially the set we define here. Right? So now you can follow the same rationale and derive the dual of the conic program. It is nothing but the lambda should be in the dual cone of K. And then this equality has to hold because after you dualize the constraint, X is an M constraint, you have to let the equality to hold strictly, right? Yeah, so note that for LP, K is self-dual, right? So let's think about which set has a non-negative product with y greater than or equal to 0. Right? It is a set itself, right? If you, let's think about it for a sec, right? Consider the first ortho here, right? The dual cone means the vector has a non-negative product with any of the vector here, right? Of course, if you pick any vector in the first ortho, the angle is less than 90 degrees, right? Then it has a non-negative product. But if you pick a vector outside the first ortho, you can always pick a vector that has a negative product, right? Because the angle is greater than 90 degrees. Right? So that's why LP is self-dual, and then you recover LP duality, right? Using conic duality. Okay. And duality is also symmetric. The dual problem is also conic, and then the dual of the dual is equivalent to the primal. You can try to show that. And then I will show some of the result of conic program very quickly without a proof. If you want to raise some rigorous proof, you can go to the references, right? So for conic program, just like in linear program, right? You can try to understand those theorems using the theorem we already told you in linear programs, right? So we also have weak duality because by construction, the Lagrangian dual is a lower bound, right? So that's why we have a weak duality. Right? If you consider the primal feasible solution and the dual feasible solution, the primal always greater than the dual. Okay. And then there are also some conditions, just like in linear program, there are some conditions under which strong duality will hold. Here are some conditions. The first is saying if the primal is bounded below and strictly feasible, meaning that this equality holds strictly, then the dual is solvable and the optimal values in the problem are equal to each other, right? So this condition is similar to the condition saying like in a linear program, if either the primal is solvable or the dual is solvable, and then we have strong duality, right? And this is the same thing. If the dual is bounded above and strictly feasible, then strong duality hold. The other condition is assuming at least one of the problem is bounded and strictly feasible, then the primal dual pairs is a parallel optimal solution to the respective problem, if and only if the following conditions hold. Well, this is nothing but the two conditions we introduced in the previous lecture. One is the primal equals to dual, the other is complementary slackness we talked about, right? I will not show the proof of this because I want to spend most of the lecture on introducing some particular applications of conic programs. Any questions so far? Okay, so yes.
I know we kind of went over this last time, but it's come up again. So I know the dual is kind of you're rephrasing the primal, but like opposite. Why is that helpful rather than just solving the primal? Because ultimately now we're kind of looking at two different problems that are, or looking at the same problem in two different ways. Yeah. Why don't we just look at one way? Why do we look at the
So that's a very good point, right? So let's say, first of all, from a theoretical point of view, it is, of course, of theoretical interest. Second, from a practical perspective, right? Let's say you are only interested in solving a problem. You are not interested in theory or algorithm or anything like that, right? So from a practical perspective, you want to get to know how far you are from the optimal solution, right? So if you keep running a primal algorithm, you still don't know how far you are from the global optimum, just based on the primal solution, unless you hit a point where you say, I check the optimality condition, it holds, right? But maybe even if the optimality condition does not hold, right, you are already very close to the optimal, or you are already satisfied with the solution you currently have, right? But then the dual give you such guarantee, right? So if you have the dual feasible solution, maybe I'm okay with 10% gap, then I should stop. I shouldn't be wasting my computational resources anymore. That is my practical way.
Solve the dual, it tells you how far away from the true minimum you are in the prime.
Yeah, so the theoretical true minimum, right? The dual is a lower bound. You cannot get better than the objective of a dual feasible solution, right? So that's one practical application. The other is some of the algorithm relies on the dual, right? If you take a look at the simplex algorithm, it does not rely on the dual, right? But then for most of the, let's say, most efficient conic programs and then the efficient general convex nonlinear programs, they are primal dual algorithm. You need a dual in order to solve that type of problem, right? And for some of the problem we introduced in this lecture, you do need to rely on the dual to invent an algorithm per se, right? And those algorithms are polynomial. Actually, one interesting concept is a simplex algorithm is very fast, but it is not a polynomial algorithm. Although linear program can theoretically be solved in polynomial time using the interior point algorithm, but interior point algorithm is a primal dual algorithm. Simplex is not, right? But simplex is not polynomial. Okay, yeah. Any other questions? Yeah. All right, so now in the next 45 minutes or so, we will give you a few specific examples of conic programs, okay? And then I will focus on the second order conic program and another program called semi-definite programs. And then we will briefly talk about two less commonly used conic program called exponential cone and power cone. Okay, so now first, what is a second order cone? Right. So this is a geometric representation of a second order cone. Right? Algebraically, it means you take the square root of x1 squared and x2 squared. It has to be less than equal to t is like the z-axis here, right? This is t, right? It is less than equal to t, right? So then you are essentially looking at, I shouldn't say it is a cone, but yeah, it is the cone you are most familiar with, like an ice cream cone, right? That's what this object is. And then horizontal sections of this set are like a disk with radius alpha, right? If you set t equals to alpha, then you essentially have a circle with radius alpha, right? Now, note that second order cone is a 3D object here, right? We have x1, x2, and t representing the set of a cone. It is a 3D object if you have x1, and x2, and t. Now, if you consider any arbitrary dimension, then second order cone can be represented as an n+1 dimensional set, where the first n dimensions are denoted as a vector x. The last dimension is denoted as one scalar t, right? And it says the norm of x is less than or equal to t. That is a second order cone in n+1 dimension. Okay. Any questions regarding the definition of this set?
So the second order part comes from that norm being given.
Yeah, so yeah, exactly, right. So that's what it means by second order, yeah. Okay. Any other questions? It's just two norm of a n-dimensional vector being less than or equal to the last dimension, right? So geometrically, you can think about this shape here. Okay. Yeah. Now, what is a dual cone of a second order cone? Right? Because if you want to consider second order conic programs, right? Then if you are interested in the primal problem and the dual problem, then we need to show what is a dual cone of a second order cone, right? So I will show you this proof very briefly. Right? Let's think about for 1 second why the dual cone of a second order cone is also the second order cone itself, right? Maybe geometrically you can get some intuition from the picture there, right?
Because 90 degrees?
Yeah, exactly, right. So because if you look at this cone, it's roughly 90 degrees, right? If you go outside this 90-degree cone, then you can find a vector that has a negative product, right? And then if you are within the 90 degree, it's just like in the first authent, right? You are essentially rotating the first authent a little bit, right? And to form this cone. But then that is sort of the intuition. We need to show that rigorously, right? And in order to show that, we need to show two things. One is, recall the definition of the dual cone is all the vector v such that the inner product of v and u is greater than or equal to 0 for all u in the set K, right? And then we want to show the dual cone is essentially the cone itself, right? So let's define, the original set is defined using x and t. Maybe we, for the sake of the argument, to not confuse the notation, let's define this set K1, which is, let's define it using y and s maybe, right? Which is the two norm of y is less than or equal to s, right? So we need to show that the dual cone of this set Kn is K1, right? K1 is, I just replaced some letters to avoid some confusion. Okay. Now, in order to show two sets are equivalent, right? Usually the trick is that you show one set is contained in another, the other set is contained in the first set. Let's first show the following. Maybe let's go back to this color. So first show that K1 is a subset of K star. Okay, so how to show K1 is a subset of K star, right? The idea is you pick any point in K1, right? It must have a non-negative inner product with any point you picked from Kn, right? That's by definition. Okay, so let's say we pick any arbitrary point for all y and s in K1. And then let's pick any arbitrary point x and t in this Kn we defined below. Right? This is without loss of generality. You pick to any arbitrary point from this cone. And now let's consider the inner product of these two vectors, right? Because we need to show their inner product has to be greater than or equal to 0. Right? So that is nothing but x transpose y plus s times t. Right? Okay. So we know that s and t must be greater than or equal to 0, right? Since s is greater than or equal to a 2 norm, t is greater than or equal to a 2 norm, right? So that it is trivial. This term is greater than or equal to 0, right? Now let's consider x transpose y, right? The only thing we need to show is the absolute value of x transpose y is smaller than s times t. Then we are good. Because x transpose y can be either positive or negative, right? If they are negative, then you need to show they must be smaller than s times t, right? So let's think about the absolute value of x transpose y, right? So if you want to consider the absolute value of x transpose y, you can consider x transpose y squared, right? What is this term? Now, how do we relate x transpose y squared with these 2 norm conditions? Right? There is one famous inequality. Does anyone remember that? What is that inequality called? No? Right, so remember what is the geometric interpretation of x transpose y? Right, this inner product of 2 vectors, right? Yeah, it's projection of one vector to another. Essentially, it's the norm of x times the norm of y times cosine theta. Right? So if you consider 2 vectors x and y, x transpose y is essentially x, y times the angle between them, right? Right. So therefore, x transpose y squared must be less than or equal to the norm of x squared times the norm of y squared, right? That's what is this inequality called? Have you studied that before? Cauchy-Schwarz, right here. So it's called I don't know if I spell it correctly. Yeah, anyways, yeah. So therefore, x transpose y is less than or equal to x norm squared times y norm squared, right? And then we know that since they are belonging to, so they belong to this set separately. The norm of y is less than or equal to s, norm of x is less than or equal to t, right? So therefore they are less than or equal to s squared t squared, right? Okay, so therefore x transpose y times plus s times t, this term must be greater than or equal to 0 because of Cauchy-Schwarz. Okay, so now we have showed if you pick any arbitrary point in K1 and arbitrary point in K, their inner product is greater than or equal to 0. That's why for all these elements in K1, it must be in the dual cone, right? Because all the elements in K1 satisfy the definition of a dual cone, right? So now this is not complete yet, right? Because we also need to show if a vector is outside K1, then it violates the definition of the dual cone, right? Okay. So the step 2 of the proof is if you have some point y such that y and s such that the 2 norm is greater than s, right? Then you should pick a point in the original cone such that it violates the definition of the dual cone, right? So which point you should pick to show this violation? Right, remember you have a sort of a 90-degree thing, right? So if you want to show it violate this 90-degree, you should pick a point that is the other way around, right? That would be saying like you should pick a point minus y, right? So you could check if you pick this point minus y and the 2 norm of minus y, right? It is in the cone, it will violate the definition of the dual cone, right? It is just some algebra you can check yourself. Okay. Any high-level questions? Yeah. Yes.
What do you mean by minus y?
Yeah. So minus y is supposedly yeah. So let's think about this concept here, right? If you pick the idea is you have a point here. For example, here it is not in the cone, right? You want to show if you pick a point here it will violate the definition of the dual cone. It will have a negative product with one of the element in the original cone, right? So which one you should pick? I would pick a vector that is sort of negative to the original vector. Then it will be, the angle will be greater than 90 degrees, right? That's why I pick minus y,
Okay.
right? Yeah, so you could check the math as well.
So is positive y the boundary?
Yeah, so you can so if positive y is here it's not in the cone, but then you should pick the here the y is x1 and x2 here, right? So you should pick the other way around, but let it lie in the cone, right? Because you need to pick a point in the cone for it to have a negative product, right? Yeah. Okay, so there is another concept called rotated second order cone. The idea is very simple. You have a cone. This is a standard second order cone, right? If you push it 90 degrees and push this cone down to the x2 and x3 axis, this is called a rotated second order cone, right? You could check if you want to represent this using equation, it is 2 times x1 times x2 greater than equal to x3 squared. Okay. I mean, there is nothing fancy here. Just rotate the original cone. Okay. And then a generalization of rotated second order cone to n plus 2 dimension is the following. You have the first n dimension being x, then the last 2 dimension you call it x, y, and z. Then the x transpose x is less than or equal to 2 times y times z, where y and z are both greater than or equal to 0. Okay. And then you could check this definition in 2D. This is a generalization of the concept to n plus 2 dimension. And then, of course, there should be some mapping between rotated cone and the original second order cone, right? Since it's just a rotation of the original problem. Then you could do this very simple trick. Here's you have a rotated second order cone. You could do a linear transformation and transform it to the original second order cone, where you can think about x being the first n dimension, and then 1 over square root 2 y minus z is the last dimension of the vector, right? So you could maybe define w equal to x, and then this term t equals to the right-hand side, and then you could check. It's very simple to check. It is a rotated second order cone, right? Yeah. We talk about the standard second order cone and then the rotated second order cone. How do you represent in a more general way? So typically people represent, when people talk about SAOC constraint, they talk about a fine transformation of the original variables. You can think about you transform x using ax plus b, you transform x using c transpose s plus d, right? So then the first m dimensions and then t is the last one dimension, right? And then you can represent this linear transformation using the same format as a standard second order cone, okay? And what can this notation represent? It can represent several different types of constraints. For example, if you have a quadratic constraint where Q is a positive semi-definite, you can represent this convex quadratic constraint using the second order cone form. Okay, so this is, you could check this is indeed the original constraint by expanding this two norm into a quadratic constraint. Okay. Yeah, so here it shows you a generic representation of second order cone constraint. So that means if you are interested in writing a second order conic program, right, there are some solvers specialized in solving second order conic programs. Then you should write your constraint in this particular form that will be recognized by the solver. It is a quite general form, right? And then you can show things like linear program, convex QPs, convex QCQPs can all be represented as SOCPs. We just show, the convex QCQP can be represented as SOCPs. Right? So if you have a convex objective, you can always take that convex objective and put that into the constraint. Yes.
So for linear programming,
Yeah.
when we express it in standard form, we also specify that x needs to be greater than or equal to 0. Is that not required for the conic form?
Yeah, so if you have a standard form, a standard form of the LP is different than the standard form of the SOC, right? So here they use a different definition. You don't need to specify x greater than or equal to 0 here. Okay, yeah. So this constraint, inequality constraint will take care of that. Yeah. Okay, and then briefly, let's talk about two other conic programs. They are not so often used, but then I just want to know you to know they exist. Right? When you see that in the literature, you don't get nervous. Yeah, that's the whole point. We won't talk a little bit too much details about that. So what the exponential cone is the following. So you can think about this problem in 3D. Right? X, Y, and Z are scalars. What is the left-hand side? You can think about it as a perspective function of an exponential function. Right? Remember what a perspective function is. You divide the argument by y and then you times it by y again, right? Yeah. So this is a perspective function of an exponential function. Remember, the perspective operation keeps convexity of a function. If the exponential function is convex, the perspective function of an exponential function is also a convex. And then this set is the epigraph of the perspective of an exponential function, right? So we in the second lecture, we talk about the epigraph of a convex function is a convex set, right? That's a connection between convex functions and convex sets. So therefore, this is a convex set, right? And then, it is not a proper cone because this set is not closed. We have this constraint y strictly greater than 0. So therefore, it is not a closed set because at y equals to 0, this term is undefined, right? But then you can always take the limit and so forth. To get the closure of the exponential cone, we need to add this particular set here, saying like when y equals to 0, x less than or equal to 0, z greater than or equal to 0, essentially it is, let's say, x less than or equal to 0, the y equal to 0, right? So that's perhaps, yeah, it's not shown in this figure. It should be a line here, right? Yeah. Okay, so what functions can you represent using exponential cone? Yeah, of course, you can represent things like epigraph of exponential function. You just set y equals to 0, and then you can also represent hippograph of a log function, right? So hippograph is the other way of defining the kind of like an antonym of the epigraph, right? So t less than or equal to a concave function is a convex set. And then you can also represent things like entropy function. Yeah. So I'm not going to the details of this because I want to spend more time on the other problems. So this is called the power cone, which is the absolute value of y is less than or equal to x raised to the power of alpha 1 times x raised to the power of alpha m and so forth. And then all the alpha has to be greater than 0, and then their summation has to be equals to 1, right? And then you can show some examples of power cone here. Yeah, this is not very commonly used. Now, I want to dedicate the rest of the time to positive semi-definite cone because you will see in a lot of literature, people talk about semi-definite programs in optimization, and it is still a sort of an unsolved problem nowadays in optimization. Okay. So what does positive semi-definite cone mean? So think about a matrix X, right? So we are not talking about a vector here. So X is a symmetric matrix, right? And it is saying this matrix X is positive semi-definite. Okay, so that's what this PSD cone mean. And then what is the dimension of the variables involved in a PSD cone? Right. So if the matrix dimension is a p by p symmetric matrix, right? Since it's symmetric, then the upper triangle equals to the lower triangle and so forth, right? So therefore, we are dealing with p times p plus 1 over 2 number of variables in a positive semi-definite cone, right? For example, in 2D, you can show this positive semi-definite cone is actually equivalent to a rotated second-order cone. Okay, so let's show about this, right? So this is a 2D constraint, right? And then this constraint is saying this 2 by 2 matrix has to be PSD, right? What is the equivalent condition for a matrix to be PSD? Yeah, you could check the eigenvalue, but then a more direct way you could do is check all the principal minors of this matrix, right? All the principal minors has to be greater than or equal to 0, right? So what are the principal minors of this matrix? It is x, right? X is greater than or equal to 0. Z is greater than or equal to 0, right? And then you calculate the determinant, it has to be greater than or equal to 0, right? That is x times z minus y squared over 2 is greater than or equal to 0, right? So this is nothing but the rotated second-order cone. Okay, you can check the definition in the previous slide. But in higher dimension, it is more expressive than second-order cone. Right? I will show you later on how do you represent a second-order cone using a PSD cone. Okay. So now let's review some properties of the PSD matrix before we talk about semi-definite programs, because you do need to know those properties in order to understand it better, right? Most of those facts I already talked about it in the review of linear algebra and calculus, but then just refresh your memories here. Okay. So let's say we denote n by n symmetric matrix by S superscript n. What is the inner product of two matrix? It is equal to the trace of V transpose W, right? If you take the inner product of two matrix, it is a trace, and then nothing but you take the dot, it's like a dot product in the vector space, right? Where Vij times Wij, the summation over all the I and j. Then a matrix is positive semi-definite if and only if you take any vectors in Rn, z transpose x, z greater than or equal to 0, and all the eigenvalues of x are non-negative. Also for PSD matrix, there exists matrices that is of dimension r times n, where r is less than or equal to n. And then X can be decomposed as a VV transpose. This is a property of the PSD matrix. And then we denote the positive semi-definite cone by S plus, and then the positive definite matrices by S plus plus. Okay. And then just to review briefly, eigenvalue decomposition. Right? If A is a symmetric matrices, then you can decompose A by Q times lambda times Q transpose, where Q is an orthogonal matrices, right? Q contains all the eigenvectors of matrix A, and lambda is a diagonal matrix with eigenvalues of A on the diagonal, right? And also remember QQ transpose equals to the identity matrix. Now let's introduce a new concept called pseudo-inverse. Maybe we didn't talk about in the linear algebra review. Okay. We know that if a matrix is full rank, you can take the inverse of that matrix, right? But then when a matrix is not full rank, there is no the inverse doesn't exist, right? So therefore, people define something called pseudo-inverse to generalize the concept of inverse matrices. Right? Okay. For PSD matrices, there is a special way to define or calculate pseudo-inverse. You can think about the way as following, where for a PSD matrix, you can use eigenvalue decomposition. So this is nothing but lambda I times the outer product of the eigenvectors. Right? This is nothing but eigenvalue decomposition. And then the pseudo-inverse of matrix A is keeping all the eigenvectors, right? But then take 1 over lambda I for each of the eigenvalues. So this is defined as the pseudo-inverse. Okay. And then you can try to multiply the pseudo-inverse with Q. And what did you get? What you get is ones on the non-zero eigenvalues in the diagonal. Right? So if you have an inverse, the inverse multiply that matrix give you the identity matrix, right? But this matrix is not full rank, right? You can only get 1 over lambda for the non-zero eigenvalues, right? For the zero ones, the lambda doesn't exist in the first place, right? So therefore, you will get sort of a low-rank identity matrix with ones corresponding to the non-zero eigenvalues. Okay, so that's what is called a pseudo-inverse for a PSD matrix. Now, just show you very briefly another theorem in linear algebra. Have some of you heard about this Schur's lemma? Okay, yeah. So it is related to the properties of PSD matrix, or how do you check PSD properties of block matrices? Okay. So let's consider a matrix written this way, where P is you can think about if the matrix is symmetric, we are going to divide them by, so the total dimension is n plus p, right? So you first consider the n dimension, this is p dimension. And similarly for the columns, you divide it by n dimension and p dimension, right? So both q and P are square matrices of dimension n and P respectively, right? Of course, they are, if the original matrix is symmetric, P and Q are also symmetric, right? And then S are the sort of the off-diagonal matrices, right? Since the matrix is symmetric, then here we have S, here we must have S transpose, right? Because the matrix has to be symmetric. Okay, then here comes the interesting part. How do you check this matrix is positive? Let's just restrict ourselves to positive semi-definite, right? So this lemma is saying, instead of checking this matrix is positive semi-definite, you can check the following easier condition, right? So 2 is an easier condition to check than checking this whole matrix is positive semi-definite. So what is the second condition? It is matrix Q is positive semi-definite, right? So this matrix is positive semi-definite. Of course, I mean, Q is part of the principal minor. It has to be PS, matrix is corresponding to the principal minors, and then it has to be PSD. And then the other condition is less trivial. It says P minus S transpose Q pseudo-inverse S has to be positive semi-definite. Right? So you could sort of decompose the PSD property of a big matrices into PSD properties of two smaller matrices. That's what this theorem is essentially about, right? There's another condition saying that all the columns of S has to be in the range space of Q. For now, you can just ignore this condition because that complicates things. When Q is full rank, this condition holds automatically. Right? So you can just remember if Q is a full rank matrices, you only need to check Q is PSD, and then this P minus S transpose Q inverse S is also PSD. Okay. Yeah, so that's sort of the idea of Schur's lemma. I want to introduce that because we will use this lemma in one of the concepts I will introduce later, right? So what are the implications, right? The math is not so intuitive. You can sort of try to prove that if you wish. But then the important part is when should you use this lemma, right? Let's say you have this on a cheat sheet, and then when should you use that, right? So the implication is it gives you a condition to check the PSD property of a block matrix, right? If you have a big matrix and then you want to show it is PSD, then you can show that two smaller matrices are PSD respectively, rather than checking the big matrix, okay? Yeah, so it sort of highlight the relationship between the definiteness of a block matrix and its sub-matrices, okay? Now, just very quickly, SOC is a special case of SDP. Right? Remember, the SOC constraint is a norm of x less than or equal to t. You can show using Schur's lemma. This constraint is nothing but you put t here and then identity matrix here and so forth. This matrix is PSD is equivalent to the SOC constraint by applying the Schur's lemma. Okay. So therefore, SDP is more sort of expressive than SOC type of constraint. Okay. Probably I wouldn't have time to show the proof, but then if you are curious, you could read the proof here. So we already said the dual cone of the linear program is the cone itself, right? The dual cone of SOC is SOC itself, right? And then for PSD cone, the dual cone of the PSD cone is also the PSD cone itself, right? So there is a short proof I wrote here. You could, if you are curious, you could read that. It uses the property of the trace, okay? Now let's talk about some applications of SDP, right? So let's suppose you can write the PSD cone in a conic program, what you can get from that, right? So the first application is you could minimize the largest eigenvalue of some, this is called like a linear matrix equality. right? So here, all those F matrices are symmetric matrices, right? They are given, and X are X1 all the way to Xm are scalars, right? So you can think about this F of X as a linear combination of a number of matrices, right? So if you say, if you consider this problem, what it means is it tries to bound this matrix F of X by gamma times identity matrix, right? In other words, it tries to bound the largest eigenvalue of matrix F of X, right? And then you minimize over the gamma. It finds you the largest eigenvalue of this function F of X. And similarly, you can maximize the smallest eigenvalue of F of X, right? Or you could minimize the eigenvalue spread between two matrices, right? The same matrices, actually, as long as you bound the matrix F of X. Okay, so those are sort of the applications. You may be wondering who really cares about the largest or the smallest eigenvalue of a linear matrix inequality, but there should be some applications where you are interested in this type of problem. Okay, yeah. Now let's see. Yeah. So another application of PSD or semi-definite programs is it is used as convex relaxations for quadratic problem. Right? We will talk about this again when we talk about global optimization. Right? So here, let's look at this particular problem, right? Which is called a quadratic unconstrained binary optimization. You will find it especially familiar to you if you work on quantum computing nowadays. People work on this type of problem because this problem can be solved by a quantum computer. So what is a quadratic unconstrained binary optimization problem? Here, all the variables xi's are binary variables, right? So xi is 0, 1 variables here, right? And the objective is a quadratic function of x plus a linear function of x. Okay, so how do we solve this problem? Where q is not positive semi-definite, right? So even if you relax the x variable to be continuous, the objective is non-convex objective. Right? Q is indefinite, right? And then this qubit problem is NP-hard in general. Okay. Now, where does semi-definite programs come into play when we try to solve this type of problem? The semi-definite programs will give you a very strong continuous relaxation of this problem. Okay, so when we solve I will come back to this point later on. So when we solve a problem with integer variables, how do you solve this problem, right? Because integer variable inherently it's a non-convex set, right? And then this problem is even harder because even if you relax integer variables, the objective is also non-convex, right? This Q matrix is not positive semi-definite. So in research, what people cares about is how do you come up with relaxation? So relaxation, you can think about relaxation as I have a non-convex set, then I find a convex set that is bigger than this non-convex set, right? Then I can solve this convex problem to provide a bound to the original non-convex problem, right? If you make the feasible region of the original problem larger, you are going to have a better objective function, right? Yeah, you bound a smaller set by a bigger set. The bigger set will give you a better objective function. So semi-definite programs are used as that convex relaxation for non-convex problem quite often. Okay, so how do you relax this problem to be a semi-definite program? Here's the trick. Okay, so let's consider the binary variables xi equals to 0, 1, right? So now I introduce another lifted space variable, right? Capital X. So capital X is a matrix variable, and then it is a symmetric matrix, right? And then I define xij equals to xi times small x times small xj, right? So this equation is nonlinear, right? Because it is a product of the original variable. You define each element of x as the product of two variables. And then xi squared equals to xi. Why is that? Yeah, because it's 0 or 1, right? Xi can only take 0 or 1. Therefore, 0 squared is 0, 1 squared is 1, right? So that's why this constraint is equivalent to this constraint, right? The 0 and 1 are the two roots of this equation. Okay? Now, if you consider all the definitions for all the n and j is essentially this equation here, where the capital X is XX transpose, right? And then the diagonal element of X, which is x1 squared, and then it should be equal to X, right? So these two definitions are equivalent. So here I did nothing but introducing a new variable, capital X, right, to represent the product of Xi and Xj, right? So if you represent the product of Xi and J, you can replace a nonlinear term using this capital X here, right? But then you still have this nonlinearity here, right? You remove the nonlinearity here, but then reformulate that using this nonlinear constraint. That's what you did, okay? But of course, this constraint is still a non-convex constraint, right? So how do we relax this constraint? We relax these equations by a PSD constraint, okay? So if this constraint holds strictly, of course, the PSD constraint hold, right? Because X minus XX transpose should be equal to 0. And of course, 0 matrix is a PSD matrix. So therefore, this constraint is a relaxation of this nonlinear constraint. You can think about this as a convex relaxation. Okay. So now, with this convex relaxation, you can solve. Oh yeah. So here it is the lifted non-convex problem. All right. You have x equals to xx transpose. Now you relax this constraint by x greater than equal to xx transpose. Right? Now, according to Scher's lemma, you can show that this constraint is equivalent to this bigger matrix being PSD. Okay. Now, this is called the semi-definite relaxation of the cubo problem, where you get rid of the binary variables, you get rid of the non-convexity in the matrix Q, right? Because now you have a linear function in the objective Q times X, and in the constraint you have a linear equation and a PSD constraint. It is also convex. Okay, so that's sort of the trick to derive the PSD relaxation of a cubo problem. And people have shown that this relaxation is sort of bounded, right? You cannot get worse than, if I remember it is 1.13. So 113% worse than the original problem. Right? It was like a remarkable result in combinatorial optimization. They show that a convex problem can bound a non-convex problem with very good gap. And then the proof was using even some probabilistic argument. Yeah. This paper is by Gomez and Williamson. If you are curious, you could take a look at that. Yeah. Now, let's see, any questions here? Right? again, I will revisit this concept again, right? If you have a non-convex problem, you can have a convex relaxation. Here, the convex relaxation happen to be a PS semi-definite programs. Okay. Yeah. Now, let's see how many slides I have. Okay, I have 2 more slides. Let's talk about this real quick. So how do you solve an SDP? Okay. One way to solve the SDP is using a very simple cutting plane algorithm. It is very easy to understand algorithm. You can implement that as long as you know linear algebra and then you know linear programs. Okay. So let's think about this as a hierarchy of linear program. Right? You have an oracle of linear programs you can already use. How do you solve the SDP? So this is what is called a cutting plane algorithm. Right? So let's suppose we have this particular problem where you start with X is a semi-definite matrix variable. Right? X is a positive semi-definite, and then you have a linear function, and then maybe you have some linear constraints. Right? But then we cannot deal with this PSD constraint. Right? Suppose you only have an oracle of linear programming solver. So let's start with M linear constraint on X without this PSD constraint. Now you have a linear program, you can solve it. But then after you solve the linear program, the X may not be positive semi-definite, right? Because you just remove this constraint. Okay. Now, what we will do is we will compute the eigenvalues and eigenvectors of the current solution. Right? Remember, the current solution you got is by removing the PSD constraint, just take a bunch of linear constraints, right? So if all the eigenvalues are non-negative, X hat is feasible and fast optimal, right? Because you remove the PSD constraint and solve a relaxed linear program, and X hat, the optimal solution you got, happen to be PSD, right? Then you are done, because even if you ignore that constraint, you already satisfy that constraint. You don't need to add that constraint, right? So if not, for each of the negative eigenvalues, right, and its corresponding eigenvector, you add a linear cut Vi transpose X Vi greater than or equal to 0, right? Because some of the eigenvectors correspond to negative eigenvalues, right? That remember X hat must violate this constraint, right? For negative eigenvalues and its corresponding eigenvectors, you have Vi transpose X Vi to be less than 0, right, for the original X hat variables. But then if you add this constraint to this linear program here, it will cut off the X hat, right? Because X hat violate this linear constraint corresponding to the negative eigenvalues and eigenvectors, right? Now you add this constraint to the linear programs and repeat, right? Yes?
When we take that cut, is the X that's used, is that your original guess X?
Yeah.
Because
So
we're trying to exclude the solution X hat.
yeah. So the eigenvalues and eigenvectors are calculated from X hat, right? But then you use the eigenvalues to add a cut corresponding to the original X variables, right? Yeah. Because you know that X hat violates this constraint. You want your next X hat to obey those constraints, right? So that's why you add this cut, okay? And then you keep adding linear constraints until you find, the solution you got satisfy the PSD constraint, then you can stop, right? You can use some sort of tolerance to determine when you are terminating, okay? Yeah. So that's a very simple algorithm, and then people use that to add SDP cuts in some of the quadratic program solvers. But no one uses this to really solve an SDP. If you want to solve an SDP, you wouldn't use this algorithm. But then when we talk about global optimization, people use this similar scheme to add what is called linear cuts to approximate the PSD cone. Okay, so finally, forget about the theory. If you are just interested in solving conic program, which solver you should use, right? So if you are interested in solving second-order conic program or mixed integer second-order conic program, you can just use Cplex or Groovy. And then if you want to solve general conic programs, the solver called Mosaic is the most commonly used conic solver. It can handle all the conic program we talked about today. This COPT is a Chinese solver that is really good recently, and then it can also solve SOCP and SDP problems. For all the other solvers, you can refer to these two links I posted here. Then most of algorithms for conic program are variants of the interior point algorithm. We will talk about the interior point algorithm in the next few lectures. Okay. So this is the bullet point I want to highlight, right? So although SDP is convex, right? Theoretically, it can be solved in polynomial time, but in practice, solving SDP is extremely slow. Okay, so it's even, empirically speaking, it's even slower than some of the NP-hard problems. Okay, because you are solving a finite size problem, this asymptotic bound doesn't really matter much to you. Right? So typically, we are talking about SDP with around the matrix equals to 100 to 1,000. That's the problem size we are talking about for SDP. That's why there are a lot of research going into SDP. It is very slow, but it has very strong theoretical properties. So there are many references. The first one is a classic textbook on conic programs, and then I refer to a few other references to gather together this lecture. You could, if you are curious, you can take a look at some of these references. I won't